So as Martin said, I will talk about tropical homology and discrete value field, and this is a work in progress with Emiliano Ambrosi. So this work takes inspiration from two different papers. The first paper is a paper of Ittenberg, Kazarkov, Kalkin, and Zarkov. That for your own sake, I will just say IKMZ during the talk. And this article is about tropical homology. And the second source of inspiration is a paper of Foster that studies the Galois action in the tropicalization. So I think the best way to start is just giving one of the main results of IKMZ. And then from that, understanding which direction you can go if you want to extend the result. So one of the main results of IKMZ is the following. You take a variety X inside the projective space over the field CDT. And you ask that the tropicalization of X is a smooth projective tropical variety. And under this hypothesis, what they managed to show is that the Hodge number of X equal the dimension of the tropical homology of the tropicalization of X. So what is interesting from my point of view is that when you do a tropicalization to some variety, you have a degeneration of your algebraic information, and you end up with a bunch of combinatorial data. So in general, if you go in the tropical world, it's not easy to say something back to the algebraic world. And here, under this hypothesis, the information that you get from a combinatorial point of view are enough to get back something like the dimension, the Hodge numbers of X. So in general, what you may expect is, given this tropicalization process, what we can say from the point of view of the tropical world about the algebraic world, algebraic geometry world. And I want to focus in this talk about these two aspects. So the first, I already said. Is linked to this combinatorial data that you may use to get back information on the algebraic world. And the second is focusing on the field you're working on. Okay. Of course, I've written too much already. I plan to just blackboard. Oh, so maybe just let me write here. Okay, so one direction you may go towards is to look at other fields. And while you start to look at other fields, what happens is that you ask yourself arithmetic question. Okay, I will be precise later. And in the process of answering to one, you ask yourself something about the arithmetic flavor of your problem, and you try to answer to that as well. So this is just an introduction, so to have the general idea of what we would like to do. So I need to give you some definition first, and I want to talk about which field I'm interested in, and what I mean by tropicalization. Okay, so for me, we will work on a complete discrete valued field. Oh, discrete. K, I will denote them by K. What they are the fraction field of some discrete valued ring that I will denote by A. And they come equipped with a valuation whose image is discrete, so you can think about a lattice. And what is your DVR, your discrete valued ring? It's just the preimage via the evaluation of R bigger than or equal than 0. And you have a unique maximal ideal, denoted by M. And this is just a preimage of the same thing, but open. And the last protagonist in this definition is the residue field associated to K, small k, which is just the quotient of A for the maximal ideal you have. So let's give some example. So for example, if you work under the hypothesis of I can Z, your DVR is just C with double parenthesis T. Your field is CDT, and the residue field is just C. But you can play with the algebraic closure or not of the residue field. So for example, we can also consider the same thing, but with real numbers. Or you can choose to have a characteristic different from 0 and consider, for example, characteristic P. So I'm talking about the take as your DVR, the periodic integers. We have QP as K and FP as your residue field. And last example, you can also take FP double parenthesis. Okay, so here are just some example. No, just two. Okay. And okay, so now we work with these guys, and if we consider K not algebraically closed, we have to consider if you want to define the tropicalization map, you have to consider the algebraic closure, and you have to extend and define your valuation in the algebraic closure. And the definition of this extension is the following. For some element y, extension of the valuation to k bar is just the previous valuation in the norm of your element. Okay. So now we have all the ingredients to define the tropicalization map. So the tropicalization map, you take n copies of your k bar. You end up in r copies over n. And the tropicalization map sends an element x1, xn, n pole, to component wise to the minus the image of the valuation. The minus is just a convention. Okay. So as I said, we are interested in arithmetic flavor, but now we have already a problem. So when you consider K and K bar, you can consider their Galois group. Okay, that will denote just G of K. Okay. And the Galois acts on K bar. Okay. But now that what you would like to do if you want to study the Galois action on the image of the evaluation, you cannot do that directly using the tropical map, because if you take some sigma leaving the Galois of K and you apply it component wise to your n pole, you end up with the same image as the n pole of the parting. of departure. Okay, find it. Sorry, this is like the more expensive Tolkien ever. Okay, I give you 50 euros later.
€1 from summary. €1, but it has to be from summary.
Okay. I will do it. Yeah, I have to start buying chalks like that. It's a good idea. Okay, so now remark. Trop does not keep the information, any information of the Galois action. I mean, it does. You see the trivial action. So having a trivial action is not a trivial information, but it's not super useful, right? Okay, but don't despair, because we can find another way to see the Galois action. So we will use the approach of Foster. In order to explain this, I need to tell you something about toric varieties. Okay, so our goal is to recover the Galois action on the tropical world. Okay, so we will consider toric varieties to define this. And what is a toric variety for me? Over K is a toric variety over K bar plus a Galois action of GK compatible with the torus action. So
torus always split, or is it?
Yeah, it's split.
Okay.
I mean, here not. Is not.
Oh, okay, okay. Yeah.
But here will be. So yeah, let's start from toric. So let's talk about real toric. This is the same thing. For example, when you work with a variety over R, what do you do to work with that? You work with a variety over C, plus you consider the anti-homomorphic involution action. Okay, so if you are over R, you go over C. Your Galois group is Z over 2Z, that's generated just by the complex conjugation. And with respect to the choice you make here of your variety, you will have a certain action that you get when you pass to the complex number. So let's do the example over R about the real toric. So first example, we have the one that everybody knows, R star. So this is just spectrum of Rx real points. Okay, so what happens when you pass on the other side? You just have C star. You just have to say what happens to the generator of the cyclic group of order 2. And this is just the map sending an element T in C star in the complex conjugate. Okay. Second example, S1. So you can see, you can think about it like you take the polynomial ring into variables, and you quotient by the ideal given by x squared plus y squared minus 1. Okay, so what happens when you go on the other side? You get C star plus the involution that take your T into 1 over T bar. Okay. And third example, which is a little less intuitive, is C star, okay, as the spectrum. So you have to take a polynomial ring with 4 variables. And you have 2 equations for the ideal. So you have x1 I write it, then I talk. Huh? Okay. And when you go on the other side, what you get C star square. And the action you are looking at is the action that switch T1 and T2 and take the conjugation. Okay. And there is a result, which I mean is a known result. So I didn't find the exact guy that did it, but I find the result in a paper of Kasselman. So fact, every real torus is a product of 1, 2, 3. I mean, a possible combination of 1, 2, 3. Okay. So now that we have dealt with real tori, let's deal with toric varieties. Okay. So our information from the start are some torus inside a variety y over k. And then what is this? Is a split torus over k bar inside your variety over k bar plus a Galois action. Compatible with the action of the torus. So for me, real toric varieties, algebraic toric varieties are given with this kind of information. And so, you have that the diagram where you have the action of the torus on your variety y plus the Galois action that you have from the in your variety is compatible with the torus. Okay. I will give you some example. Okay. So let's take the example we have here above. So if you take our first example here, you can take, for example, P1, okay? And the Galois action you get, the real structure you get on P1 that is compatible with the torus action is just the simple complex conjugation, the standard one. So you just take X and Y, and you send them to X bar, Y bar. Okay. The second action that you get, so if you consider P1 with this torus inside, is the real structure that switches X and Y and take the conjugation. Okay. And for the last one, I will give you two different examples. So you have that your real part is C star. So you have to imagine that is the diagonal inside this C star square. So the first example I give you is P2 with induced real structure compatible with this torus. Let's take X, Y, and Z and send them to Y bar, X bar, and Z bar. So it switches X and Y. Or for example, another variety you can consider, which is compatible with this, is P1 times P1. And the real structure you have, let's call it tau maybe, is the one that take the two generator of the two different family of 2P1 and switches them and taking the conjugation. Okay. Remark, as real algebraic variety, this 2p1 with these two different real structure are isomorphic. This P2 with this strange real structure is isomorphic to P2 with the standard conjugation as real algebraic variety. I will write conj to say standard conjugation. Instead, if you take this P1 times P1 with this action switching the two generators, this is not isomorphic to the P1 times P1 with the standard conjugation. Okay. In fact, this is the quadric ellipsoid. Its real part is a sphere, and here the real part is RP1 times RP1. Okay, so why I'm telling you all this? Oh my gosh. Okay, because now what happened that let's focus for a second on the real torus over K bar plus the Galois action. Okay, so now you have a Galois action on your splitting torus. Okay, and this implies that you have also a Galois action on the character of your torus. And if you tensorize this guy with R, you get Rn. And now the proposition of Foster is to consider this guy as target of your tropicalization map. New target. Okay. So now what happened? You consider once again your tropicalization map, and your new target is the character of the torus tensorized with R. And now you get something, a map of tropicalization, which is GK equivariant. Okay, so maybe let's see an easy example. Maybe I can switch this. Okay, for example, and of course, if you consider to start with a torus inside Y, and inside Y you consider a subvariety, let's say X over K. Then what you get a split torus in YK bar. You get X over K bar plus a GK action. And your XK bar is invariant under this action. Okay. So if you consider here, maybe you can use a color. No? Your XK bar intersecting with the torus. You tropicalize it and take the closure. So this is, for me, is the closure of this guy. you have that, you have an object, the tropicalization of X, which is also JK invariant. Okay. So let's make an example. Let's say that you have a line inside P2 over some K. Then what you get on the other side, you get a line in P2K bar plus an action. Okay. So for example, let's say that when you tropicalize, you use a JK tropicalization. If you get, for example, let's say that the action of your torus is the standard one. So your torus just send T1, T2 into T2 bar, T1 bar. Okay. Oh, sorry, I inverted them. Then the action you get on the character of the torus are just the identity. You send E1 into E1 as the generator of Z2 and E2 in E2. So the action you see actually on the tropicalization of the line is just the identity. Instead, for example, let's assume that we are in the case in which your torus acts switching the two generators. In this case, the action you see on the lattice Z2 is a symmetry with respect to 1, 1, to the direction 1, 1 of the diagonal. So here you have E1 goes in E2, E2 goes into E1. Okay.
So you don't need to dualize the character method, or I mean, usually you end up in co-character.
So if you look, for example, at the equation here, you dualize. So for example, let's say this is given by a matrix, then you have to take the transpose to see that, for example, the equation of L is invariant. I'm used with the other one that has already been. I'm not yet a master of erasing German blackboards. Okay, but before getting in the serious business with maybe some theorem, I want to tell you something else that will be useful. So remember that our goal is to kind of extend the theorem of ICAM-Z, okay? So now what we have an action. So you start with a subvariety inside some other variety. You get in the tropical world a subvariety of a tropical variety with an action. So you have an action on the tropicalization of L here, of your Galois. It can be trivial, it can be not trivial, or something more complicated. But now what does it imply this? It implies that you have also an action on the tropical homology of your subvariety. So if you remember the theorem of ICAM-Z, you were comparing the Hodge number of some X with the dimension of the tropical homology of trop of X. Okay, so now we have a new information. We have the tropical homology of trop of X plus an action. Okay. So what we would like to do, can we say something in the algebraic word side? Of course, you cannot say directly something on the Hodge numbers because you don't have Galois action on them. So the point will be now to find a candidate, a geometric object to compare with our tropicalization of X. And then we will say something more precise. But before doing that, so the goal to keep in mind is to find a geometric object to compare with the tropicalization of X, on which acts some Galois action. Okay. And before doing that, but this is what you have to keep in mind, I have to tell you something about the Galois action of the field K and the Galois action of the residue field small k. Okay. So once again, this is a complete discrete valued field. And associated to it is there is this residue field small k. And in general, we always have a surjection from the Galois of k into the Galois of small k. Okay. And the kernel of this the sequence is what is called the inertia of the action. Just to give you some example, just to make you understand that it's not clear always how is the inertia and how it can act on the same geometric object that you have in your set of tools. So let's take K equals CDT, right? Our IKMZ example. So what is the Galois of CDT? It's just the at Z. So you can just think that it's generated by a loop of the puncture disk. And then what is J of the small k? So small k, remember, it's just C. So actually you don't have anything here. You have the trivial group. So what does it mean? It means that the inertia has all the information of your Galois. Okay. Other example, if you instead of C you take R. What do you have? Now you have that your Galois of the residue field is Z over 2Z. Your inertia is Z at, once again. And the middle guy is a semi-direct product of Z at with Z over 2Z. So I'm saying all of this because the geometric object that we will find to compare with the tropicalization will have an action of J small k on him. Instead, the tropicalization of X will have an action of J big K. So in general, if you have two geometric objects that looks like the same, and you have two different Galois groups acting on him, so on one you have this one and the other one you have this one, you cannot directly compare them unless, for example, the inertia acts trivially. Okay, so I will give you another example and then I will tell you something more about this trivial action of the inertia. So the last example, for example, we can do QP. The residue field is FP. Okay. So in this case, the Galois of the small k is just Z at. And the inertia and the Galois of k becomes more and more complicated. So I will not write them because you can give them as generators and relation, but they're really complicated. So let's just say very complicated thing. So you're starting to see that if you want to compare these two guys, and here you have something, and here you have something hyper complicated, it's not easy to do. Okay, that was my point. Okay. And just let me say that so we are looking at action on the character of the torus. So if the inertia acts on the character of the torus trivially, we say that the action is unramified. Okay. It's a good moment if you have a serious doubt about what I've said. If you have a question. And equivalently, asking that the inertia acts trivially is equivalent to ask that there exists an ramified extension. Oops. Yeah, it's not. Can I try a new one? There is an ramified extension of your field K. With the property that the index of K prime over K equal the index of big K prime over K. And K prime is in K. And such that your K prime is the smallest extension you can take, such that you get a split torus. So smallest extension such that the torus of K prime is a split torus. Plus you have a Galois action of K prime acting. And this, what does this imply? It implies the following. So when you consider the action of GK on the character of your torus, so you can take GL of your torus, the kernel of this action is given by GK prime. Okay. So asking for the inertia to act trivially, it means that the action you see on the character of the torus is actually given by the Galois of K prime over K. Okay, maybe it's a good idea to give an example about this. Yeah, okay. So just to have an example in which your Galois does not act as Z over 2Z. Let's see an example in which the Galois acts as a Z over 3Z. So we start with a sextic, so a curve of degree 6. I can give you the explicit polynomial, but it's not useful. Okay, inside P2, and your field is QP. And this is a sextic over the closure QP bar inside P2, QP bar. And the action that you get is a Z3 action. And this Z over 3Z action is given by a ramified extension of QP of index 3. So the action of all Galois group of QP is just given by this guy, okay, factors to this guy, and you just have to describe what happens for a generator of the CK group to understand how is the action on the on the tropical world. Okay, and the generator of Z over 3Z that you get as this shape is a matrix 2 by 2 acting on Z2, the lattice of the projective plane. And so just to make you understand what's happening, the action you're looking at over the projective space is the action that sends x, y, z to z, x, y. Okay, is an order 3 action. Okay, and so now give me a second to draw the sextic. So what is the action that you see of the Galois and the tropicalization? So you have your sextic, tropical sextic. Almost there. Okay. Okay, so you just have to think a graph embedded in R2 if you want. The degree that remembers that you have a sextic is just given counting or the number of horizontal lines or vertical lines or diagonal lines. And the number of cycles you see encodes the genus of your curve. So here we see 10 cycles, and the genus of our sextic is 10. And what does the action there when we tropicalize? I will draw it. Yeah. Think about a good picture, okay? Okay. So your action rotates. Let's say that you start here, you rotate 1/3, you rotate another 1/3, and you go back. So let's give an enumeration of your cycles. Okay. We consider gamma are your 10 cycles. And this guys generates so the homology class in the homology group I'm writing just encodes the psychologically the H1 you see in the normal homology. Okay. You can describe the action of sigma that you see here. You can translate it also in an action that you see on these cycles that generates your H01. And the matrix that gives you the action is a 10 by 10 matrix that can you explicitly write. So let's call this guy B. You have 3 times B. And then you have the central cycle, which is fixed by the action. So you have just one here. And if you want to describe the dual of this guy, so if you look at the H10 of top of C, the action will just be the transpose of A. Okay. So let's go back to our problem. I will leave this example for later.
So is this a coincidence that the action H01 and H10 is pretty much the same?
Right, since it's a curve, I mean, you just have H00 and H10 and 01, and you have the Poincare duality, and you just, I mean, if you know the action on one, you know the action on the other.
Yeah, okay, but I mean, in a higher dimensional example, would you see the same pattern?
Yes, I mean, you just have to be careful on the numbers you're taking, but yes.
Okay.
Yeah. Okay. So let's go back to the fact that we want to find a geometric object to compare with the tropicalization of X. So if we go back to the paper of ICAM-Z, the first thing they do to prove their theorem is to consider the generation of, so they put their variety into a family. Okay, so you have your X inside Pn, and now you can consider to be over any discrete values field, not only CDT. And the first thing they do is consider a family such that the general fiber is X. Okay, so you can imagine to have this on a puncture disk. You have the whole family on a disk. And the special fiber that they construct with the hypothesis they have is such that all the combinatorial data that you have here are actually encoded in the tropical variety that you get from doing trop of X. They have the same combinatorial data. In fact, you can describe the tropical arrangement of the special fiber looking at the tropicalization in the following way. So for example, to a vertex in your tropical variety of X, given by X, will correspond an irreducible component of X0. Okay. And all type of intersection that we are considering a semi-stable degeneration, so the special fiber is normal crossing. All the intersection you have of any of the reducible components are given in the following way. So for example, if you have two vertices in the tropical variety connected by a line, you will see in the algebraic world two irreducible components intersecting in one point. And same goes for higher dimension. And in particular, you can describe a stratification of your special fiber using this description coming from the tropical variety. Okay. And I just want to say that here you have already your geometric object you can compare with the tropicalization of X. The only problem is that when you work on the special fiber, you work on the residue field. So this is just vector K, this point, small k. Okay. So here comes the problem about comparing the Galois action that you will have on the tropicalization of X and the Galois action of small k that you will have on the special fiber. Okay. That's why I told you about when you can compare these two actions. Okay. Yeah. But I recall you that we're not only looking for a geometric object, we have to understand when we can compare the tropical homology of trop of X with some other homological group. Okay. So we have to go a little deeper in the proof of IKMZ before I can tell you about where we will compare these two Galois action. So now you have this family, okay, and you know that this guy somehow encodes the information of trop of X, okay, and on the other side, you know that in the theorem of IKMZ, you have the odd numbers of the generic fiber. Okay, so you need a way to pass from somehow the homology of the special fiber to the homology of the generic fiber if you want to compare them. And this is done via the use of a spectral sequence, which is the Steenbrick spectral sequence. I will not be precise on the indices, but morally, you have the following. You have that some sum of some homology of a subject you take. You remember that I told you you have a stratification of x0 in terms of the tropicalization of X. And here the homology you are taking is given by some skeleta of a certain dimension of the special fiber, and you are over Q. And this spectral sequence will give you, so let's say that you have PQ, the homology of the generic fiber over Q. Okay. And what does it mean to have this spectral sequence? It means it's the same thing to give in a filtration of this homology of the generic fiber, such that the pieces you need to compute this homology, this is, yeah, let's say n, are given by the quotients of this filtration, 2 by 2. And you're lucky because this spectral sequence that generates at the second page. So actually this guy is just E2. Okay. And now it comes the results. So these pieces read the homology of the generic fiber. So they will read the odd numbers somehow. And now one of the main results of IKMZ that is needed to prove the old theorem is that if you take the right coefficients of the second page and you take the dual, because here we have homology, but on the tropical world we have homology, this guy is isomorphic to the tropical homology QP of trop of X. Okay. And now it's here that we can talk about Galois action, because here we have a Galois action of GK. And here, since we are on the special fiber, this guy is some piece of homology of the special fiber, we will have G of a small k. Okay. But of course, we cannot directly speak about Galois action here because we still have the standard homology, right? The Ram homology. So what you can do, what we have done with Emiliano, is considering, so let's say that in an old homology theory, you have enough formalism to try to do the same things that somebody else has done somewhere else, okay? So you have to find the right way to phrase it. If you want to look at some kind of Galois action here, you need to work with a Talc homology. So you have to do a base change over K bar. And you have to work with QL coefficients, where L is different from the characteristic of the residue field. And this is the Rappaport zinc spectral sequence. Okay. Okay. And also this guy now will have a Galois action on it, right? So here, since we are considering the Talc homology, we will have now a Galois action of small k. On the other side, we have a Galois action of big K. Okay. So what we would like to do, we would like to have this theorem, but in an equivariant way, GK equivariant way. So finally, I can give you the result. Okay, let's do this. So first of all, we consider K as a usual, and then you have your variety inside P and K. This is the same thing, taking the variety over K bar inside P and K bar, plus a Galois action of GK. Okay. Okay, and if you assume that, so here I'm taking the standard tropicalization for now, and then I will consider the other one. Trop of X is a smooth projective tropical variety, tropical variety. Then first thing you can prove is that you have this isomorphism, but considering the talc homology. Okay. And if you assume that the inertia of the action of GK acts trivially on the character of your torus inside Pn, and you consider not the standard tropicalization, but the equivariant tropicalization, then you can also show that this isomorphism that I call the F is JK equivariant. Okay. Before giving you a corollary of this, just to be complete about the extension of ICAM-Z theorem, I will give you another theorem, and then I will go back to a corollary of this result. Okay, theorem 2. So if you are in the white hypothesis, so I'm not considering equivariant tropicalization, but just the standard one. And I don't take any possible K, but I take QP or a finite extension of QP. Then you can show that the Hodge number of X equal the dimension of the tropical homology QP of trop of X. And here, the difference is that if you want to prove this, starting from that result, you need p-adic Hodge theory. Okay, in ICAM-Z they use Hodge theory. Instead, here you need to use p-adic Hodge theory. Okay, p-adic. Okay, and as last thing, I would just say that as a corollary of theorem 1. So in general, given a variety, it's not easy to say what the Galois does on the homology of this variety. But under the hypothesis in orange, so we are same orange hypothesis. You can say something, you can recover a part of the action of the Galois on the generic fiber, on the action of the semi-simplification of the generic fiber from the action you have on the tropical homology. So I will write it down. So the semi-simplification of the action of GK on the talc homology, and here I'm assuming any K, not only QP, on the talc homology of the generic fiber can be computed from the action that you see of the Galois group on the tropical homology of Tropox. So going back to this example of the Sextic in P2, what I'm saying is that if you take the first homological group of the Sextic and you take the semi-simplification of the action of the Galois on this group, this can be described as the action on the sum, direct sum of the homology group where the sum of P and Q gives me back 1 in this case. Okay. So explicitly in this example, the action of the semi-simplification of the action on this group will be given by a 20 by 20 matrix of this form. You have A transpose, and 0 everywhere. Okay. So I think I will stop here.